Hello students, welcome back. Let's begin section 4. Homogeneous linear ODEs with constant coefficients. Here's a general form of the equation, and here's a general solution. Take a good look at this general solution. Please note that this is a linear combination of the functions of the form t to the some power times the exponential. Where are these exponentials and powers coming from? Well, in order to help you understand, I did some color coding. They're all coming from the characteristic polynomial, or more precisely speaking, the factorization of the characteristic polynomial. By the way, is this possible? The answer is yes. Please recall, every polynomial can be factored completely all the way down to linear factors in complex number system. This fact is known as the fundamental theorem of algebra. And if you need some further review about the fundamental theorem and the complex numbers in general, please go back to lesson 1A, one of the preliminaries there. Otherwise, let's come back here. My next question is, what is the degree of this polynomial? If you look at the left-hand side, the answer is clear. It's n. Of course, everything came from the original linear ODE, and that has order n, so clearly the characteristic polynomial must have degree n. But then again, look at the right-hand side. What's the degree? The degree must be the sum of all these powers. In other words, we get this. m1 plus m2 plus and so on, they have to add up to n. So here's a conclusion. The characteristic polynomial q of s has k zeros, lambda 1, lambda 2, lambda 3, and so on, all the way over to lambda k. In general, they are all complex numbers, and each lambda I has a multiplicity, m1, m2, m3, and so on, and the multiplicities, these m values, must add up to n, the order of the original linear ODE. Keep that in your mind, and let us analyze this solution further. Now, as I did my color coding, these exponential parts are coming from the 0. You see, the lambda value here corresponds to this lambda value for the first batch, and the second batch, third batch, and so on. In the last batch here, this lambda value here corresponds to lambda k from the kth factor. So all those exponentials are coming from the zeros. Now let's look at the power part. T to the 0 power, and then first power, second power, third power, and so on, all the way over to m-1 power. That corresponds to the m value, the multiplicity. And that was the first batch, and then second, third, fourth, and so on, kth batch, exactly the same. So the powers corresponds to the m value, the multiplicity, and the exponential corresponds to the lambda value, the 0. How many are there? In the first batch, there are m1 functions, because that's a multiplicity, from 0 to m-1. And second and third, all the way over to the last batch, again, m value, mk. Add them all up, there are precisely n functions here in this expression. So this is a linear combination of n functions. Okay, that's the general solution. And let's consider some examples. We'll prove it, yes, but it can wait. Example first. By the way, here's a little bit more fancy expression with sigma notation, if you like sigmas better. Okay, let's forget about the proof for the time being, and let's go to an example problem first. Here is a 6th order linear ODE with constant coefficients. Consequently, its characteristic polynomial will be a 6th degree polynomial. Don't be intimidated. I'm going to use computer algebra system to factor it. So we have these. So first factor, blue. Second factor, red with multiplicity 3. And the third factor, this is quadratically reducible. And I worked out a little bit. I rewrote it as a complete square plus square form. And furthermore, I decomposed it in the complex zero expression. 1 plus 2i, 1 minus 2i. There should be complex conjugate of each other. Okay, now how many factors are there? 1, 2, 3 factors in terms of real. 1, 2, 3, 4 factors in terms of complex. Doesn't matter too much. The blue factor here has multiplicity 1, and then we have one function. We have t to the 0 power multiplied, so it does not appear. How about the second factor here? We have multiplicity 3, so we have these 3 functions. They all have e to the negative t power, because the 0 here is negative 1. We have s plus 1 equal to 0, so 0 is negative 1. How about the power part? We have t to the 0 power, first power, and second power. Now how about these complex parts? We have these complex exponentials. Now, if you don't like these complex exponentials, then you can convert those into reals like this. So the real part here becomes exponential, and the imaginary part there becomes sine cosine. Our textbook author always does it this way, the second way, using real expression. Me personally, I prefer the first expression, this one. I'm in minority, I have to say, but if you go to graduate school, actually more people do it this way than that way. Now, why do we have this compatibility between exponential of complex versus sine and cosine? That's because of these. And for the detail, I'm going to refer to lesson 1A again, one of those preliminaries. Okay, all right, that completed the example problem. And the moral of the story was the factorization of the characteristic polynomial did the trick. Okay, all right, now let's prove it. But then again, I'm not going to prove the entire theorem. I'm going to prove only one direction. This one, I'm not going to prove it here. Maybe I'll come back and do it later, or maybe I'll skip altogether. Let's see, in terms of the level of difficulty, it's not too bad. I can do it. Yes, a little bit difficult, but I can do it. But bigger problem is the logical reason, actually. Most of the time, if not all the time, what we are doing is, given the equation, finding the solution. We are always in the forward direction. We never do it backward. If you already have a solution, that is a solution, we just use it instead of plugging it back and checking back and whether it works all the time. In general case, why would anybody bother? Except possibly, of course, for just mathematical perfection. That's why I'm not going to cover the other direction. I'll just stick to the forward direction here, at least for now. And this is something we have been doing all the time in chapter 2. We begin from the original linear ODE and take the Laplace transform. Left-hand side can be decomposed like this. You can break up all this linear combination. Right-hand side is 0. And if you use the input derivative rules here, all those derivatives will have this polynomial expression. And the coefficient of s to the whatever power, the highest, is always capital Y. So if you take the like terms together, then always you'll have Q of S, characteristic polynomial here. And the other part will have the degree at most n-1. This is as big as it can get. Consequently, if you solve for capital Y, you're going to get R of S over Q of S, where R is a polynomial of degree at most n-1, and Q is a polynomial of degree n, so this is a proper rational expression. And thus, we can decompose it using the fundamental theorem again, factor the denominator, and then decompose it by partial fraction. The first factor, s minus lambda 1, to the first power, second power, third power, all the way over to m1 power, the multiplicity, and so on and so forth. There are total n such fractions, m1 plus m2 plus m3 plus and so on, add up to n. And here is a Laplace inversion. That completes the proof of the forward direction. Not just proof, but also it gave you the method of solution. Speaking of method of solution, let's review it really briefly before going over to actual example problem. We just went through this Laplace transform method. You see, we did this. This is this exact thing we just did. So using the Laplace transform method, we can find the structure of the general solution. Now, what if you do alternative method here, substitution method? And it works kind of like this, but it's a bit imperfect, at least in our level. We begin with an educated guess, e to the st power, and take all those derivatives and put those into the original equation. Because of the chain rule, we get s to some power, and exponential always remains the same. And if you put everything in there, then exponential is common to everything, so I can factor it out, and what's left is a characteristic polynomial. Setting it equal to 0 because right hand side is equal to 0, and observing that exponential is never 0, so you can throw away by dividing out, you're going to get the characteristic equation. The solution of this characteristic equation, or the root, are actually the zeros of the characteristic polynomial, which are lambda 1, lambda 2, lambda 3, and so on. And therefore, we get these solutions. Y is e to the lambda 1t, e to the lambda 2t, and so on, all the way over to e to the lambda kt, because that's where we started. But then again, that's not enough. I need n solutions, but I have only k. So we need some multiplicities, and it turns out other than just this, we have all the other baggages as well for a given multiplicity. The same here. Other than just this, we have all these baggages too. Why? That's a bit tricky to prove actually, and tedious too. And it has something to do with the part that I skipped in this previous theorem here, this part. For now, let us just concentrate upon the general solution and its structure. By the way, we can simply adopt what we discussed in the previous method. As a matter of fact, we already have everything, entire structure of the general solution from Laplace transform method. And why do we have to reproduce exactly the same thing using the substitution method? We got those e to the lambda t's all right. How about the other t to the whatever times? We can simply adopt from Laplace transform method. In any case, we have the complete structure. We know all those solution methods, so let's go to example problems. Okay, let's begin. We'll probably have enough time to finish everything. The first problem is just second order, so it's easy. Let's go over this really quickly. Okay, all right. Here's a Laplace transform method. As usual, you have R over Q. And then factor the denominator and decompose by partial fraction. In general, we'll probably have, we'll probably have 4s minus 1, but I think I overdid it here, but I ended up getting 1/4 and dividing. That's okay. I can always adjust this undetermined coefficient there. In the end, I have these expressions. How about the substitution method? Well, if I plug in all those exponentials, you see, y is e to the st, y prime is s times e to the st power, y double prime is s squared times e to the st. So plug everything in and then simplify what you get. 4 times this exponential plus 3 s times exponential minus just the exponential equal to 0. And please note that exponentials are all common, so I can factor all these out. And what you have the characteristic equation. Solve it. you have the zeros of the characteristic polynomial. That's always the case, so experienced students will jump right over to characteristic equation. And then in the end, we have the same expression as before. That was easy. How about the next? Actually, this is equally as easy. Maybe you can just stop this playback and do it on your own. Okay, the Laplace transform method, as usual, you have R over Q, and you can factor the denominator, and this is not too bad because this is quadratic, but it's just trinomial. So factor it as if you factor a quadratic trinomial, except that you're factoring with respect to x squared, and factor it further, we have this. Maybe I should okay, all right, everybody can read better now, I guess. And then decompose by partial fraction. Blue goes to blue, red goes to red, and then green goes to green. Here, the characteristic value, or the zero of the characteristic polynomial, is plus and minus I. So complex roots, so we have sine and cosine there. Detail is left to the students. How about the substitution method? We can do the same thing. Y is e to the st power, and then take all those derivatives and put those in, and exponentials are common and remove them all. We have to have this characteristic equation rather, and then set it equal to 0. That is equivalent to factoring and finding the zeros of the characteristic polynomial. And we have negative 1/2 here, positive 1/2 here, and plus or minus I here. So we have this expression there. How about part C? Now don't try this with paper and pencil method. This may be a good exercise for your knowledge on computer algebra system. How do you factor this? Well, you can set up the denominator, and then you have to factor the denominator, and here's the factorization and the decomposition by partial fraction. But my suggestion is to use computer algebra system, and please study some mathematical commands. You can use this in Wolfram Alpha as well. Okay, factorization done. So we can use it down here, and then decompose by partial fraction, and then the Laplace inversion. That should be easy. How about the substitution method? Again, if you put all those substitution, you have to have the characteristic equation. So factor the characteristic polynomial and find out all those zeros. So we have -1 here, 1/2 there with multiplicity 2, and then we have 1 plus 2i, 1 minus 2i from this quadratic irreducible factor. And thus we get this. Okay, that completes this section.